Hi, so welcome to this Nordic Semiconductor webinar. Today we have a webinar about power profiling, your application, where we will talk about common pitfalls when doing embedded design and how to detect them and how to optimize your application for power consumption. We will, of course, be covering our latest release, the Power Profiler Kit 2, that was released yesterday. The webinar today will be hosted by me, Paul Kostnes. I'm a technical marketing manager with Nordic Semiconductor. I take care of a lot of the tools from our side, and the Power Profiler Kit is one of them. The majority of the talking today will be done by Christian Vilgaard. He is with our application groups. He's the project manager for the Power Profiler Kit 2. So a few practicalities before we get started. Björn has entered some comments in the chat. If you have issues with video and audio and so on, there are things that you can try to do to get things working properly. The time slot for this webinar is 60 minutes, so we are expected to close at 6 o'clock Central European time, so in 57 minutes. We will have a Q&A session in the end. We really encourage you guys to ask questions. Feel free to fill in questions during the presentation from our side, and then we will cover them at the end of the session. There is a question section in the top right corner. We recommend everybody to use this one for entering their questions. All the questions entered in the question section are anonymous. Try to keep them relevant to the topic. The topic today is power profiling. For other questions, we recommend to contact DevZone. We will, as I said, we will go through all of these ones in the end. There is a chat solution as well in the right-hand side. On the lower side, where you can see there's a lot of comments coming in now. This one is not anonymous, and we prefer that we don't use this for questions. That's because we need to monitor two places if that happens. So it's better to put everything in the question section. At the end of the event, if your questions were not answered, please feel free to enter a ticket on DevZone. This is our support portal. You will be able to search through previous asked questions and so on. Again, we have a lot of answers there already. The Power Profiler Kit 2 is already starting to get a lot of traction there as well. So we will follow up with specific questions there. The recording of the webinar will be made available through our webinar portal. So you'll be able to watch the recording again if there were things you didn't quite catch when we went through it, or if you arrive a little bit late. We will also make the presentations available for download on this on the portal, on the same portal. And with that, I hand it over to Christian, who will cover all the technical details now.
Thank you, Paul. Yes, my name is Christian Vilgaard, and I have been working a lot with power profiling tools in my time with Nordic. When working with battery-driven embedded applications, power consumption is a crucial part through the whole development process. If you have ever asked yourself how you can reduce power consumption and extend the battery lifetime without doing so at the cost of sacrificing functionality, you have come to the right place. So to figure out these questions, we also need to know which tools to use to figure out where we can find those extra milliamp hours. Today, I will go through some reasons to why your application might consume more power than you expect and how we can measure it. I'll talk about what to look for both in the code, the hardware layout, and a little bit about the choice of components for your hardware. There is a lot of ways to optimize your product to get those extra hours, days, or maybe weeks, so I have picked some common places to focus on. I'll be recommending some tools to use when optimizing your product's power usage, and I will give you an introduction and demonstration to our latest tool, the Power Profiler Kit 2, which is the second generation Power Profiler kit from Nordic Semiconductor. First, let's talk about various things in your application source that you need to make sure you take care of. There are times where just moving a line of code can give you several milliamps less current consumption. With our type of devices, that means a lot of extra lifetime before charging or replacing your power source. When I demonstrate the new Power Profiler Kit 2, I will show you some real-life examples of this. Most of the time, the first and foremost reason for high current consumption from your application is that the application is not going to sleep, or just waking up too often. This might be as simple as forgetting to go to sleep after having done the initial setups, or that the SoC is woken up from an interrupt source at intervals that was not intended when designing the application. With most embedded applications, a good practice is to do all the setup that needs to be done, then enter an infinite loop and let interrupt routines and hardware events do the rest of the work. This means that you will end your main function with an infinite loop that calls the _WFE instruction on the ARM core. The wait for event instruction will put the device to sleep and wait for an event to occur, meaning that when an interrupt is triggered, the device will wake up, handle the interrupt routine, and go back to sleep when done with that job. Forgetting to go to sleep will cause the infinite loop to be processed and the CPU is spinning as fast as it can, doing nothing at all. That is why just checking that your device is giving you the functionality you expect it to is not enough. You also need to verify it does as expected when not doing anything at all as well. Another is logging. Logging is a feature that is really convenient in the development and debugging phase of the application. But logging also utilizes peripherals that adds extra power consumptions as well, such as UART or the real-time transfer module from Seger, that uses the debug channel for communication. Turning off logging before going to production is crucial, as it is not needed by the end user and might consume a relative high amount of power. If logging is needed, it is also wise to think about when we actually need logging. For instance, you can save some states in a summary when something interesting happens, and have another trigger that logs that summary to your terminal or Bluetooth peripheral when you need it. A third reason might be that the SoC wakes up more often or before you want it to. When you have turned off logging and set the SoC to go to sleep when all tasks are complete, it might still be woken up from interrupt sources configured in the application. This can be button presses, a timer that wakes it up to read some sensor data or similar. Say that you are reading your sensor, getting your data and everything seems fine. But behind it all, the processor wakes up much more often than you intended, thus decreasing the battery lifetime of your product. You also have to consider how fast do you actually want to read the state of something, for instance a sensor. If you have an accelerometer and a gyro that's intended to give the user a real-time 3D representation of your product's position, then we need to have quite fast sampling. But most times we only want to know approximately the position, and maybe not that often. It's important to really specify the end user's need. Do you want a lot of fancy performance, or can we adjust that expectancy a little and get more battery life? And of course, having unused peripherals running that is not of any practical use. We've seen it time and time again, that a developer might do a lot of testing to begin with, turning on modules for testing and forgetting to disable the ones that will not be needed in production, or having configured something to run a lot more than needed. Plan the structure of your software carefully, so it always is easy to give it a read-through to see if there are any places where we can remove or change parameters that will utilize the peripherals more than we need. Moving away from just code, it is also important to think about that it is not just the SoC that consumes power. You will often have different sensors and power components like boost converters that might drain your battery if not used correctly. When using sensors like an accelerometer, it's important that you select devices with low quiescent current, meaning the current consumed when the device is idle. It's also the SoC's task to manage which sensors to enable at which times. Turning off a sensor when you don't need data from it is important, as it will continue to drain your battery while you have no use for it. Here it's common to use timers or, for example, buttons that wakes up your device from sleep. Enable the sensor and reads data. Do what must be done, disable the sensor and go back to sleep. As I mentioned previously, it might not even be that you need an accelerometer or IMU that gives you data all the time, from all the directions. Maybe you just want to know when your product has flipped upside down. Then you can choose an accelerometer that gives you a single signal telling you exactly this, and not all the other axes that your product don't need. Most battery-operated circuits also have some components for managing power on the board, like buck or boost converters, LDO regulators, and maybe even voltage dividers. When selecting buck-boost converters, you need to keep in mind how much power the converter needs to be able to provide. If your application can consume less power, then the buck boost itself can also consume less power to be able to deliver what your circuit needs. The same goes for LDOs, or low dropout regulators. You need to be careful in your selection of all of these. Even when selecting pull-downs and voltage dividers, you need to think it through. Say for instance, you are measuring your battery level and need to divide the voltage to be able to be within the limits of the ADC input. A simple voltage divider will do the trick, but here we need to make sure that the values are large enough to not let the battery be drained through the shunt resistor more than it needs to for proper ADC readings. Signal pull-downs are also important, as they need to be strong enough, in other words low enough resistance, to pull the line properly to ground. But if it's too strong, you might get unwanted current leakages. So now that we know some sources of battery drain, let's see how we can find them to optimize our product further. You will get a lot of information from just looking at schematics, datasheets, and source code. But to make it easier to pinpoint the different sources of power consumption, there are some tools that will come in handy. Let's have a closer look at these typical tools. Every embedded developer needs a way to program their device, and most often this is a debugger that can do a lot more than just programming firmwares. A debugger is also used for diving into how your code is executed, freeze at certain places in the code, and investigate what is going on in the SoC. A debugger like this, for instance, or the onboard debugger chips that we deliver with our development kits, can give you insight to how much memory is used, which blocks of memory, which peripherals are active at certain times, etc. Stepping up your game to a professional-grade J-Link debugger with trace capabilities, for example. We can also get real-time code coverage and profiling. This is extremely powerful, as you can see which part of the code are executed for how long, how threads are managed, and a lot more. But such features come with a downside of a fairly high price and extra routing needed on your device. To get the best insight into your code's execution, you also might need to lower optimization levels. So a debugger is useful during code development, but might not be sufficient on the end product, where you might even not have the debug lines accessible. This is why when moving over to characterizing the performance of the end product, one usually don't want to be dependent on a debugger. A logic analyzer can be used to extract the timing of your product's execution and to debug digital signaling protocols like SPI, I2C, and UART. One good example for debugging timing is to set some GPIOs at certain stages of your software and see if the timing is as you expected. It's definitely a valuable tool when your SoC is talking with sensors to see how traffic is exchanged and debugging your protocol, but it only gets us so far. Unfortunately, it's most often not very user-friendly on the final circuit board. They can be quite expensive, and they do not give any direct information about current consumption. So, for actually measuring how much power our device consumes, a multimeter will come in handy. It is used for measuring voltage and currents quite easily throughout different parts of your circuit and is a must-have tool when designing a circuit. But this also falls a bit short if we want to pinpoint what is actually using up our battery. since it will only give you instantaneous measurements with quite low detail. Even so, it can give you a good estimation about the total power usage, to give you a hint about whether or not you are within the numbers that you expect. An oscilloscope is also good for measuring both analog and digital signals, with very high accuracy and bandwidth. As it does only measure voltage and doesn't have any current measurement circuitry, you need to measure the voltage drop over a resistor in the power path of your circuit board. This means that you need to swap this resistor with regards to what range you want to be measuring with higher accuracy. By using Ohm's law, you will get the current from dividing the voltage measured by the resistance you're using. And, if you want to measure over a long time span, accuracy starts to drop, and a proper oscilloscope can be very expensive, thus not available to everyone. Then we have a power analyzer, and this is at the higher end of equipment used for measuring power consumption. It is very accurate and should be considered the benchmark tool for final qualification and lifetime estimation of the design if you have one available. It is, however, very heavy and often takes up much space and can be very expensive. A proper power analyzer might set you back a few thousand US$. This means that in general, developers rarely have access to such equipment, especially at their personal desks. With all that said, we can see that there are very few instruments that is a one-size-fits-all solution. When trying to battle the shortcomings of generally affordable and available instruments, we saw the need to create the Power Profiler Kit. We wanted a tool that was optimized for our low power devices, so we were able to make it small enough to sit on everyone's desk, cheaper than the average development kit, and it has dynamic range switching to give you better resolution over the whole spectrum instead of just within certain ranges, as I mentioned when measuring with an oscilloscope. While this was sufficient for a while, with newer devices with faster operation speeds and higher power consumption, the PPK falls a bit short, with a measurement limit of approximately 70 milliamps and a continuous sampling speed of a little below 8 kilosamples per second. It also needs an external debugger, making it harder to debug your application while doing measurements. That is why we now have launched the Power Profiler Kit 2. The new Power Profiler Kit 2 from Nordic Semiconductor supports a much higher measurement range than the previous generation. It is used to measure and analyze any embedded hardware, including all development kits from Nordic. Like before, it's supported by the Power Profiler app in NRF Connect for desktop. It is delivered with two sets of cables, one for connecting for power measurement and one for connecting to the new logic port. The logic port is a brand new feature, which can be seen on the bottom right of this image. Here you can connect your device under test or any other device and get live data about the digital states that you insert on these pins. This means that you can, for example, map some outputs to trigger when certain events in your application is happening and see it compared to the current consumption you are measuring. It's accurate down to approximately 200 nanoamperes, up to 1 ampere, meaning it supports the whole product line from Nordic Semiconductor. The PPK2 is dynamically switching its internal measurement circuitry to give you great resolution for whatever measurement you are doing. So for our cellular NRF9160DK, it will provide you with details all the way from the low power saving modes up to active GPS and modem states. With 100 kilosamples per second continuously, this makes it more than 10 times faster than the previous generation. This in turn gives you much better detail of not only power consumption, but also what is happening on your device. The software gives you the possibility to zoom into the highest level of detail. Where the first version of the Power Profiler Kit could give you a high resolution trace at some times, the PPK2 gives you an even higher resolution continuously. The PPK2 also supports using the tool as an ampermeter and a source meter, meaning that your device under test can either be powered by the 0.8 to 5 volt regulated output from the PPK2 or your own power source, such as a benchtop supply or a battery. We also made it completely standalone. There's no debugger necessary, only a USB connection to a computer, and our software package easily downloaded through NRF Connect for desktop. The Power Profiler Kit 2 is complemented by the online Power Profiler tool. This tool is based on a model of measured values, which should give a good theoretical indication of what power consumption you can expect from Nordic hardware, supporting both nRF52 and the nRF91 series. Once you have a proof of concept, you can check values from the online Power Profiler with the PPK2 values to double check that everything is working as expected. Due to a lot of environmental factors, it's a good idea to verify these numbers for your physical device in the expected operating environment. So, to wrap up why this is a very useful tool to the general developer. Being of a small form factor and non-intrusive to the final product, this can be used through the entire engineering cycle to make sure added functionality does not affect power consumption more than you expect. There's no need to book time to use the one piece of high-end expensive equipment that your company might have, since this can always be laying at your desk. This will also save you time, as you can debug unwanted power consumption right away, instead of waiting until you have taken your time to see how much better life you can expect out of your product. It's also very cost efficient, seeing as one does not need an extra Nordic DK or debugger to communicate with the computer software. And yes, the PPK2 is supported in Windows, Linux and macOS. When updates to the PPK2 firmware is needed, the software will take care of this through the PPK2's bootloader, so there is no need for an extra programmer. Alright, I will now show you a demonstration of the PPK2. For this demonstration, I will first show you the PPK2 software in general, using an nRF9160 DK that is running the out-of-the-box asset tracker example. Then I will use an nRF52840 DK with some different examples, showing how some minor mistakes in your code will impact your power consumption. I will also show you a practical usage of the logic port. So, for the PPK2 to give you anything, we need to start up NRF Connect for desktop. I have here entered a filter for Power Profiler, so that it only shows me results for this. And if you haven't installed it, this button here will show install. After you have installed it, you can go ahead and open it. As I have connected my PPK2 to the computer, it's lighting up green, and I will also get it in my device list. I have also connected an nRF9160 DK. This is now powered through USB, and I have set up the PPK2 to measure the DK in ampere meter mode. This is explained further in the PPK2 user guide, so I will not go through that here. When selecting it, the sidebar is activated. And from here, we can control everything about the PPK2. It's now lighting up blue, as I have selected ampere meter mode. And we can also change this to source meter, meaning that we will power the DUT with our PPK. And now it is lighting up red, as indicated in this corner, but we can also switch it back to ampere meter and start sampling. Now we're just getting these small current spikes, and we have an average of some nanoamps, and that's because we haven't enabled the power output. So let's toggle that. Alright, so here we are. This nRF9160 DK is running the default asset tracker example, which it comes with out of the box. And now we have some data for the full window. We see that we have some 32 milliamp average, 62 to 82 max, 7-second window, and also some calculation for the charge. While this is running, we can toggle the power, like so. And we can also pause the charge by either clicking the live view toggle up here, or if we start manipulating the chart by either panning with holding the mouse and zooming with the scroll wheel. And we can also resume the chart by right-clicking in the chart. If you don't want to zoom with the scroll wheel, you can also use these presets that we have right here. These can go down to quite low detail. So let's say we'll zoom out and look at some particular area of the chart. If I want to know more about this exact part, then I can hold Shift and left click and drag. And now I get some timing between these selectors. And I also have new calculations for this selected area. So here we can see the average, the maximum, time, and the charge for only the selection. And we still get updated values for the whole window. So I also have digital channels, which is not used right now. I haven't connected it, but I will show that later. While the chart is paused, there is a buffer filling up. So there will still be incoming data when it's paused, and you can see that from this animation in the Stop Start Sampling button. That data is still incoming. So if I now toggle Live View, the markers are cleared, but almost all of the data is still intact. We can store data for up to 2 minutes as of this time. So if I just zoom out, then we can see that we still have the old data all the way from the last power up. Alright, that's it for this one. Let's stop it and I will disconnect this and show you the next example. So for this next example, I have swapped out the 9160 DK with an NRF52840 DK, which I am now powering with the PPK2 instead of using the ampere meter mode. So there are no USB or battery connected to the 52840 DK. It's only powered by the PPK2. So I'll select it again, and now before I enable the power output, I need to change to source meter. And since this is a 52840 DK, I also want to adjust the voltage within its range, so I'll set it to 3 volts. Now I can start sampling and enable the power output. So in this example, it's a PWM driver example from the SDK, which will change between some demos when I press button 1 and 2. So by pressing a button, we can see from the current consumption that it's changed to a new demo. And for this example, for instance, it's toggling an LED 3 times and pausing, and then toggling them again 3 times. And this is clearly visible from just looking at the power consumption. But I have also connected 3 digital channels on this one. So I'll enable that and select my 3 connected channels. We can now see that we have some lines on the bottom here. What I have done here is choosing pin 1 to represent button 1, pin 2 for button 2, and pin 3 is toggling when I'm entering the main loop. So by pressing a button, we can now see that we have a toggle on the button. We entered the main loop a couple of times, and we can also see that the power consumption changed. And as we can see, that to see the digital channels, we need to use a maximum window size of 3 seconds. So I'll just click 3 seconds and live view again. I can continue to press the buttons back and forth. And we can see that this is synchronized well with the power consumption we're seeing. And we're entering the main loop every time we press the button to do some processing. So what this means is that you can easily correlate what's happening on your hardware within certain events with the current consumption that we're seeing. And here, for instance, we can see that the PWM demo is entering the main loop quite a lot. So it's not sleeping an optimal amount. We can see an average of 4 milliamps, which is quite high. And this is fading an LED one by one. If we zoom in and showing it live, we can actually see the PWM increasing and decreasing. So now that you have seen how to use the digital channels, how we can use the markers, and how we can extrapolate the data that we want, we might also want to export some data. This is done by either zooming out the window that you're interested in or making a selection. Say that I want this data set. Now I can stop the sampling and click export. And now you will have an estimation about how much time and storage space this export will take. You can choose to include the digital logic pins as single string fields or as separate fields, just by toggling these ones. When I click save, a file saving dialog will pop up, and I will be able to save it as a CSV file and open that one in Excel or some other spreadsheet viewer. Okay, so now I have opened up an instance where I have the 52840 DK programmed with the BLE app example from the SDK. And we can just start looking at it as it is in its original state. Let's zoom in a little. Alright, so we have an average current consumption over several events of around 180 microamps. We can also now zoom in and see, for instance, what's the advertisement interval. It's about 100 milliseconds. We see that we have an idle current between the intervals, which is at 14.556 microamps. And for this one, I can just disable the digital channels. And as I mentioned earlier, I just want to show you how easy it is to make a simple mistake in your code that can make a huge impact on your power consumption. So this is how the example is today. And I have made a cheating file for flashing some beacon examples. So I'll start writing the original one. We can see that we have the same power consumption in the background here, 180 microamps. And now we can try to flash a beacon example that doesn't go to sleep. In other words, we have either forgotten this one or commented it out. So now we can see that the story is a completely different one. From 180 microamps, we are now up to 6.16 milliamps. And the beacon in itself is still working because we have the radio events still. There are 3 distinct events from the radio, which is the TX packages, no RX, since this is an not connectable advertisement type of package. And this is how much just not going to sleep can do with your application. So let's see what we have in the time between the radio intervals. 6 milliamp. So from 15 microamps to 6 milliamps. This example is also doing some logging just to begin with. But let's restore the sleep and make the mistake that we are doing logging in the main infinite loop. So if I flash this one, then we can see it's even worse. Now we went from 6 point something to 7.37 milliamps. So even though we call the sleep functionality of the SDK, we are not going to sleep because the nref log will cause many events to happen and not letting the CPU go to sleep as we want it to. So now we have an idle state of 7.15 milliamps. But it's not just for doing mistakes. We can also see what's happening if we want to, for instance, decrease the interval between these radio events. This meaning that it's in its original state, and on the top here we can change from 100 milliseconds to, for instance, 500. And now we can verify that that actually did work. So we can see that if we place some markers and select this one, it's indeed 0.5 seconds. So I think this is a very good example of how you can see that minor changes to your code can impact your application significantly. And also we can see that by using 100 milliseconds interval setting, we had 170 to 180 microamps, and now we're down to just 51. So think carefully about your application's requirements, and then you can save a lot of battery time. Alright, that was all from me for this time. I hope you have learned something new, and thank you for listening in. Now it's time for some Q&A.